So last week we finished with proof that the phase transition was continuous for the FK pair correlation. So let me finish everything I want to say on FK pair correlation by telling you a few conjectures, and in particular how you can relate this observable that I defined with SLE, with conformal invariants. And then we will start a completely new chapter in the class, which is basically related to the Ising model. So that's probably the maybe third case, third part, which is conformal invariants. So remember what we did. We had a domain omega. Imagine I give you a domain omega. And we had a graph, let's call it omega delta, which was some kind of discrete version of a domain, a simply connected domain omega, with 2 points on the boundary. So imagine I have A and B like that. I had this omega delta, and basically I was taking 1 point on the boundary A delta here, and 1 point on the boundary B delta here, and this omega delta A delta B delta was a Dobryshin domain. I was calling this a Dobryshin domain, and it was in my mind a discretization of a continuum domain. So in order really to be a discretization, what you could do is, rather than looking at just a subset of Z2, look at the subdomain of delta Z2, where delta is much smaller than 1. So imagine you take a very thin mesh size lattice, and you take a subdomain omega delta, which is roughly following the shape of omega. So here, just think, let's simplify. Let's take omega to be Jordan, very smooth, and omega delta to be roughly omega intersected with delta Z2. It's not quite true, because if you think about it, if you do that, this omega delta first has no reason to be connected, second has no reason to be, the complement has no reason to be connected, etc., etc. So you have a little bit of a problem when you do like that. But let's say you take like a big subset of this, a big subgraph of this guy, for instance, the biggest macroscopic component or something like that, and it will look like omega. Okay? There is a notion of convergence in Kara-Theodori sense, but maybe it's a little bit complicated here, so let me ignore this. So when you have this set omega delta and A delta, B delta, which are close to A and B, you can consider a random variable, so consider gamma delta to be the exploration path in omega delta, A delta, B delta. So it is a random variable, and your question is, when delta tends to 0, to what does it converge? And the conjecture is the following. It's a conjecture due to Oded-Schramm. And it says the following. So if Q is between 0 and 4, 4 included, then, and if you look at omega, which is sample according to Dobryshin boundary condition. So remember Dobryshin boundary condition, I said that I would denote them like that. At PC of Q and Q. Then, so let's say this is, okay, this, let's call it gamma of omega delta. Let's call it like that. Then gamma of omega delta is converging in law to a curve which is called the SLE kappa, where kappa is equal to 8 over sigma plus 1. So remember, sigma was the spin in our observable. And just if you translate it into Q, it gives you 4 pi divided by Q minus r cos of square root of Q divided by 2. So this is a conjecture. And let me make a few comments on this conjecture. So the first comment, and that's actually more than a comment, it's what do I mean by convergence in law here? So in order to have a convergence in law of random variables, you need some topology on the set on which the random variable is taking values. So the random variable here is taking values by definition roughly in continuous curve, non-self-crossing continuous curves from A to B in omega. So I need to give you a topology on this thing, and I'm going to say that the distance between two curves, distance between gamma and gamma tilde, so these are the deterministic curves. It's going to be just the infimum over sigma 1 and sigma 2, or phi 1 and phi 2. These are increasing functions of the Hausdorff distance between gamma phi 1, gamma tilde, and phi 2. So what am I saying? I have two curves, gamma and gamma tilde. So they are just, parameterized functions valued in omega, starting, so gamma, if gamma is a function from, say, from T1, T2 to omega, gamma T1 must be equal to A, gamma T2 must be equal to B. Gamma tilde is another guy from, say, T2, T4 to omega. So what I'm doing, I'm trying to find the best possible reparametrization of these curves in such a way that you get the minimal Hausdorff distance. Okay? You know what the Hausdorff distance is. Okay, good. So this gives you a distance between parameterized curves, and this induces a notion of convergence in law. Why? Because as soon as you have a distance, you have a topology. If you have a topology, you have a notion of continuous functions, and then you can speak of convergence in law. So that's the first thing. So in particular, it basically really tells you that you are getting closer and closer as random curves. Second thing, I didn't tell you what SLE kappa is. So SLE kappa is called the Schramm-Loevner evolution. We are going to have a class on that later on in the year. And the important thing that I want to say on that is that, so it's going to be SLE kappa in omega AB. And an important property of SLE kappa is that if you take, of Schramm-Loevner evolution, is that if you take a conformal map phi to another domain, so this is phi of A, this is phi of omega, and this is phi of B, then the law of phi of SLE kappa in omega AB, well, this is going to be equal, or if you want this thing, is going to be equal in law to SLE kappa in phi of A, phi of omega, phi of A, phi of B. So what does it mean? It means that as random curves, the SLE kappa here is just the image of the SLE kappa here. Okay? So this, should not come as a real surprise, at least if you take, say, phi to be a rotation by pi over 2. Because the lattice itself is a square lattice, you see very well what is going to happen. If you take the rotation by pi over 2, of course, the curve that you get in this domain and the curve you get in this domain, you can couple them even in such a way that this one is always just the rotation of this one. So of course, when they converge, the continuous object has to keep this symmetry. But what I'm saying is that it's true for any conformal map, so for any rotation, for any dilation, and even for any map which is holomorphic and one-to-one. So in particular, this tells you something very interesting on the model itself. It tells you that if I take here the model I take the scaling limit. It's the same as taking the scaling limit of the model here. This is called, when you take delta to 0, is called taking the scaling limit. If you take the scaling limit here, it's just the image of what you would get if you take the scaling limit here. Even though the lattices themselves, of course, at the discrete level, it's completely wrong. And if you have a lot of information, if you have a lot of symmetries, so since SLE is conformally invariant, you get a lot of information on it. And let me give you a few examples of things that you could compute when you do these things. So the first thing you could compute, for instance, is you can take a domain like that, say A and B, and you can look at the probability. You take a small epsilon like that. The probability that your SLE is going to go through this thing, through this small. So it's going to tell you what is the probability for the SLE to do that. It goes from A to B, but what is the probability that it goes in this small box? So because there is so much symmetries, when you have a very symmetric object, usually you manage to encode it with a simpler object. And this is exactly what is happening with these SLEs. They are encoded by one-dimensional functions, in fact by Brownian motions. And you can really study very well these things. And in particular here, you will get that the probability is behaving like epsilon to the sigma, where sigma is the spin that we had before. But this tells you something interesting, because this tells you, remember, the arc from A to B in the random cluster model is free, and the arc from B to A is wired. So the interface, this SLE is the limit of the interface, so it's the limit of the separation between the cluster connected to the top and the dual cluster connected to the bottom. So in particular, what you get is that this is roughly the probability if I have a path going like that in the random cluster model. And this, when delta tends to 0, you get that. So what does it give you? It gives you that the probability roughly of having, if I take a box of size n times n, probability of having a path between epsilon n and n like that is roughly like epsilon to the sigma. And from there, it's very easy to deduce that then you actually predict that the probability to get from 0 to distance n should behave like 1 over n to the sigma. Just tune epsilon equal 1 over n. The story is more complicated than that, but let's just assume that. So it gives you exactly, for instance, an exponent. It gives you the one-arm exponent on the boundary. And this is the simplest computation you could do, but you have many other computations, because in fact, these SLEs, thanks to this conformal invariance, you can compute the Hausdorff dimension of the curve, you can compute the probability of, to give you another example, you could also you take a box of size epsilon, and something of size roughly 1, say 1/2, and this is 1. You could compute the probability of doing something like that, for instance. You go there, you go away, you come back, and you go away again. What is the picture that is going to be corresponding to that in the random cluster model? It's going to correspond roughly to something that looks like that. It's going to be the existence of 2 primal arms and 2 dual arms going through the thing. So if you remember percolation, this is a 4-arm event. So if you can compute that, you can compute the exponent of the 4-arm event, and this was very, I don't know if I told you a little, I told you a little bit about the scaling relations, how you could deduce nu and beta from alpha 1 and alpha 4. So here, for instance, you would have a way of computing alpha 4 for percolation, if you would get this for q equal 1. Okay, that's actually exactly how it's computed. So this is a very useful thing to get. It's not just nice, it's actually useful. But now what is the relation to our observable? So I told you that the observable satisfies these local relations, which look a little bit like discrete holomorphicity. And there is a good reason for that, is that if you define, so conjecture, well, maybe definition before, Let's define an observable on the vertices. And the observable, we are going to define it like that. We are going to say, take f of v. So we have a vertex v. And remember, we are on the medial lattice, so we have 4 edges A, B, C, D around it. Take f of v to be equal to 1/2 of f of A plus f of B, just half of the sum of the guys. You should not do that on the boundary, but let's say inside, let's do that. On the boundary, there is a nice way of defining what you want, but it's not exactly this way. And let's divide it, so let's call it maybe small f, f delta. Let's divide it by square root of twice EB, where remember EB was the last edge in your domain. So this thing has two impacts. The first one is EB is of modulus delta over square root 2. So it has a renormalization impact. And also EB has a certain orientation. So it also tells you the orientation of the thing. So this is, we are going to call it F delta is called, or I call it, is called the renormalized parafermionic, vertex parafermionic observable. Okay, so it's roughly, looks very much like the edge parafermionic observable, and the conjecture by Smirnov is that if Q in 0, and here I'm going to put 4 excluded, and because in fact at 4 something slightly different occurs. And if you take, then you have that F delta. So F delta is, and you take omega AB. So F delta is a function defined on omega. So by the way, it's a function which is defined only on the vertices of the graph omega delta. But you can extend it very easily. What you do is that for every face, just draw a diagonal. There you define it, and on the edges here, everywhere you define it as the linear combination, the convex combination of the value here and here, or the value here and here for these edges. So then you get the observable, a definition of the observable on every edge. Every point of an edge, and then inside you just do barycenters. So you have very nice, otherwise you can change a little bit the definition. You can extend it to really all the faces, like really everything which is inside your set omega delta. And therefore you can speak of a uniform convergence on every compact. And it should converge to the following. It should converge to phi prime to the power sigma, where the sigma is the spin, and phi is any map from omega AB onto the strip of height 1. And this is phi of A, phi of B. And this is phi of omega. So here, if you are awake, you should say, okay, there is not a single map from this set to this set. Well, right? Because you have 3 degrees of freedom in Riemann mapping theorem, and here I used only 2. I want to send A, so I want to send omega to the strip. This is always possible. Then I have 3 degrees of freedom. I send A to minus infinity, B to plus infinity. So I get 2 degrees. I still have a 3rd degree of freedom. So there are actually many maps like that. But you will notice that they are easy to get. It's a map plus, just a shift plus an additive constant, which is real. But I'm taking the derivative. So all these maps gives you the same answer here. So this is a conjecture. And the way you would prove it, if you would like to prove it, is actually very nice. What you would do is you would say this thing, what is the solution of this guy? What is this phi prime to the sigma? Well, it is a unique solution of the following boundary value problem, where you take omega, A and B, and what you do is that you ask for an holomorphic function in this domain satisfying some boundary conditions. And the boundary condition is that you want, on the boundary, you want f of v to be perpendicular to, this is going to be the orthonormal, maybe it's parallel, sorry, the orthonormal vector at v, except that you put it to the power sigma. So you should be careful when you put the power to the power sigma, because this, I mean, you are in the complex plane, but you just take an analytic, the only thing that you need to define it in an analytic way through the boundary, when you go along the boundary. This doesn't define completely your function, because you see that lambda times your function is also going to satisfy the same boundary value problem. But you have a renormalization plus a renormalization here, so some renormalization here. At B. And actually, it's fairly easy to check that this observable satisfies exactly this property. So this observable satisfies the right boundary conditions, the discrete version of that. As I said, we have this kind of almost discrete holomorphicity inside the domain, so it's very natural to expect that this guy, when delta tends to 0, is going to converge to the solution of the continuous value problem, which is this one. You can try to guess why this is. This should be phi prime to the sigma. So this is how you would like to do it. The problem is that the best way would just say that, okay, I take a discrete version of this boundary value problem at the discrete level, which is going to be being orthogonal to the discrete orthonormal vector. It should be orthogonal, sorry. Well, okay, it's one of the two. I never remember. It depends. You need to do something. So you should do that. You could do that, sorry. The problem is that we do not know that f delta is the unique solution of this boundary value problem. If you take a function satisfying this boundary value problem and just the properties that f delta, the relation that f delta was satisfying, there are many such functions. So if we would have a stronger notion of, if we would really have discrete holomorphicity, maybe there is a unique solution to this boundary value problem. And if this is the case, then you have really a chance to use just analysis to prove that then this, since f delta is a unique solution to this boundary value problem, probably I can prove abstractly, forgetting about f delta, that this the unique solution of the boundary value problem is converging to the solution of the continuous counterpart. And actually, that's what was done in one special case by Smirnov. And he proved that for Q equal 2, the conjecture is true, in the sense that it is actually a theorem. And just as a corollary, but you have to work. It's not a simple corollary. You also get, so this was, or whatever, with many people, that then gamma delta tends to SLE 16/3 for Q equal 2. So you can deduce from that the convergence also of the interface. And let me finish this chapter by just telling you why Q equal 2 is special. So for Q equal 2, sigma is equal to a half. Therefore, e to the I sigma times the winding of the curve at an edge EB is always going to be belonging to a certain vector depending only on E, let's call it V of E, times R. In the sense that you will know the complex argument modulo pi of your observable, of this quantity. Why? Because simply the winding will always be equal to a certain deterministic winding plus pi z. Plus 2 pi z, sorry. So when you divide by half, you will get this result. Notice that if there will be a sigma for which, for instance, sigma equal 1 would be even better in this case. You will really very well know the argument. But sigma equal 1 is SLE 8. It's actually Q equals 0. And this is corresponding to the uniform spanning tree, which is indeed known to be conformally invariant. So it's not very surprising that these two models are exactly the models for which you know. So since you have that, therefore, the observable itself belongs to V of VR. So now you have a number of vertices of omega delta complex equations. And you have number of edges of omega delta, real and non-variables. So that's a big difference. So now they are real. So I mean, it's not completely clear that you are safe, because you could really imagine that these complex equations, they also degenerate somehow, but it's not the case. If you are lucky enough, it's not the case. So it's a sequence of kind of small miracles that make it that this, now you have twice more. Each complex equation corresponds to 2 real equations, and you can make the thing work. There is a unique solution, and so on and so on. So this you will see with Stas or with, I don't know who will do it. You will see that really in the second term that we can really prove conformal invariance. So this will be done in the second term. So I'm not going to do it now. So basically in the class where you will do conformal invariance, you are going to speak a little bit about SLE to be able to even state the results. And then you are going to do, well, probably the 4 only models where you know conformal invariance, which is loop arrays random walk, which you are going to see is going to be very different. Easing, which is exactly this one. Percolation, which you are going to see the proof is very different, but it's beautiful proof. And either dimers or a uniform spanning tree, I don't know, or maybe you will do both if you are lucky enough, I don't know. But these are really isolated cases somehow. And here you see why it's isolated. There's really something miraculous happening at Q equal 2. Okay, well, so if you really want to work hard on something very, very difficult, try to do any other case than Q equal 2. But this is really, I would not really recommend it to try, but I recommend to succeed. This, if you manage to do it, that's very good. Okay, that was the end of this part. So big conjecture and few results. Chapter, that's chapter 4? 4? Yeah. 5? Right, 5. Random current representation. So here we are going to change a little bit our way of looking at things. Our goal is to go away from this planar case. So we want a representation. So we have, notice that we have a bunch of representation for the Ising model, right? We have the random cluster representation. For the planar Ising model, we have the loop representation of the random cluster representation. So actually we have even a mapping to a 6-vertex model for those who remember. We also, maybe you saw actually in the class of Ivan, the high and the low temperature expansions of the Ising model. Here it's yet another one, okay? It's a random current. And this is maybe the least known and the most powerful, so that's... Okay, so we are not going to restrict ourselves to nearest neighbor because just it's not going to simplify anything there. So I'm going to take Ising. Remember I had defined coupling constants. So I'm going to look at Ising with coupling constants Jxy. And I'm going to be on ZD. There's no restriction there. And Jxy is positive, and it's translational invariant. I'm also going to denote, so now I'm going to drop the dependency in Q because I will not speak about Potts model anymore. So I'm going to denote mu plus or minus of 3 beta for the measure in infinite volume model, infinite volume, yeah, for plus, minus, and 3 boundary conditions. So I'm not going to say 1 and 2 for the boundary conditions, but plus and minus. And notice, why is it well defined? Well, the fact that you have coupling constants, if you want to look at a random cluster representation of this, is absolutely no problem, right? Just you put an edge between every vertices of your graph. Okay, so it's a complete graph, except that then the weight of an edge is not always 1 minus e to the minus beta. It's going to be 1 minus e to the minus beta jxy. Okay? So the farther you are, the smaller the probability of being open, basically. And then when you do that, you can take an infinite volume version of that and define an infinite volume measure. Because a priori, it's not completely clear that you have that. Okay? So it can be defined via coupling with Fk. Okay. And the last thing I'm going to define, because, I mean, just a notation, sigma A is going to be the product for x in A of sigma x. And this is for any set A, which is a subset of the vertices. Just a notation. Okay. So let me start by the definition of the random current representation. It's going to take a little bit of time, but you're going to see that after that we are going to be able to deduce a lot of things. So take a graph G. What I love with this representation is that it's really, do the simplest thing possible, it works. You don't need to go to define very complicated concepts. You just go with the simplest possible, and it works. So definition. And the definition of a current, so a current N on a graph G is simply a function N, which goes from the edges into the integers. That's just what I'm going to call a current. And let omega G be the set of currents. That's the first question. Now, a current is going to be associated to a set of sources. So a source of N is a vertex X such that sum for Y in so the edges now, because I mean that's actually all the pairs of vertices, okay? Because I really think I'm not nearest neighbor anymore. So it's all the pairs of vertices. So over Y in Vg of nx1 odd. So I'm going to be a source is if when I sum all the currents emanating from this vertex, I get something odd. And let's set partial n to be the set of sources. That's the definition. It looks like an absolutely meaningless definition at first sight. And let me just, before I actually give you the connection to the Ising model, tell you why we call it current and source. So imagine you take a sourceless current, meaning that you have no sources whatsoever. how can I obtain easily a sourceless current? What I can do is I can look at a loop not self-avoiding, just a loop, and look at its occupation time, how many times it went through every vertex. This gives me, so by taking the occupation time, it gives me a sourceless current. Right? Simply because every time you arrive at a vertex, you need to exit this vertex. So so it implies very easily that you get a sourceless current. If you do a union of loops, you also get a sourceless current. So union, so one loop. So union of loop also gets sourceless current. And in fact, it's fairly easy to see that it is an equivalence. Any sourceless current can be obtained as a union of loops. How do you do that? Start from a sourceless current, pick a vertex for which pick a vertex for which there is a non-trivial current going out from it, and just take this edge with a positive current, and remove one to the current. You arrive at a new vertex, and notice that now you are at a vertex where you have an odd number for the currents, because you removed one and it was even before. So you always have a way to carry on. So you carry on, you go one more step along an edge where the current is positive, you delete by one. And you carry on like that. What is going to happen is at some point you are going to come back at your vertex. That's the only way you can stop. Otherwise you cannot stop. You arrive at this vertex, you just define the loop. Maybe you spend several times on the same vertex, it's okay. But you get a loop. So you remove the loop from your current, and now you can iterate. And you are going to peel like that your current. These loops like that, they are interpreted in physics as what they call eddy currents. And that's why this thing is called a current configuration. Just if I take a current with two sources, A and B. Then, how do I get these currents? Well, it's the same idea. What you're going to say is you start from A, and you do this peeling process that I described. Either I close a loop, or I'm going to finish at B. When I have done that, I have a path from A to B, and a collection of loops. So a current with sources at A and B is simply a collection of loops plus a path from A to B. This is going to be useful because this tells us that if you have sources at A and B, necessarily A and B are connected by the currents. It's just a necessity. Okay, what is the connection to the Ising model now? The connection, so first proposition, so next notation is we are defined Z of G beta A to be just Z3, say, to be just the sum of the exponential of beta times the Hamiltonian at sigma for any sigma is plus minus to the V of G. So it's kind of, that's the partition function, and you add sigma of A. So if you take A to be the empty set, you just get the partition function. It's the sum of exponential of minus beta times the Hamiltonian. Okay? But what I'm saying is that I'm defining something that depends on A by saying that here I'm multiplying by sigma of N. Okay? So for instance, if I want mu G beta 3 of sigma x sigma y, if I want to write it in terms of this Z, what is it? Just the ratio between this quantity and this one. right? Just the definition. So this is a quantity of interest. It's just going to be a convenient notation. And now the first proposition is that, and oh, sorry, I forgot, maybe add somewhere here. Okay, well, so first proposition is let W beta of n to be the product for every xy of beta to the nxy over nxy factorial, and this is for every edge xy in the of your graph. So this is some kind of weight depending on beta, and the proposition is saying the following, saying for any A included in V of G, for any, we have that Z free G beta A is equal to 2 to the number of vertices in my graph times the sum of W beta of n for n occurrent on G, but with a constraint that the set of sources is A. So if you want to have the partition function, I mean this partition function with the product sigma A, what you do is you simply, up to a constant which is always the same, do a weighted sum on currents with a prescribed condition, which is that the boundary is A. The sources is A. Okay, let's make a break now, like that, or I do the proof. It's not a very long proof, and then we make a break. So, how do we prove that? So we look at this quantity, Z free of G beta A. So it's the sum over every sigma of sigma A times, instead of saying exponential of minus beta times the Hamiltonian, I'm going to write the product for every edge xy of e to the beta sigma x sigma, I mean jxy sigma x sigma y. And I just realized that because I'm used to present this for nearest neighbor, I forgot one quantity, which is you should add a jxy here, sorry. So you agree this is exactly the same as there. And now what you do is that you expand this with the Taylor series. So it's the sum of the sigma, let's not sigma A, product over xy. And here I'm going to say it's the sum over nxy equals 0 to infinity of jxy and beta jxy to the nxy, beta jxy sigma x sigma y to the nxy divided by nxy factorial. So I just expanded and called the variable nxy. Now I have sum of product of sums, so you can just exchange everything. It's going to give you the sum of occurrence. And when you exchange everything, you see that many things you are going to get somewhere the sum over the sigmas. So what you can do is remove everything that doesn't depend on the sigma. So what doesn't depend on the sigma? We have the beta jx1 to the nx1 divided by nx1 factorial for every edge. So it's going to be the product for xy in my edge of beta jxy to the nxy divided by nxy factorial, which you recognize is exactly the weight that I introduced there. And here in the product, now you have a product of things that depend on the edges, so of sigmas depending on every edge. So you're going to have a product for x in the vertices of your graph of sigma x, and sigma x occurs how many times? It occurs for all, it occurs for all edges, and it occurs to a power nxy. So you're going to get sum of nxy for y vertices. except that it may occur also once in the sigma A. So it's going to be plus a delta of x belongs to A. Okay? So all of this is what? So it's the sum over the n in omega g. You get a w beta of n. And now this sum. Let's look at this sum. Imagine that this is odd for some x. Then you are summing over every configuration a certain product. If this is odd for some x, if you get sigma, if you associate it to sigma x, which is just same configuration, but sigma x flipped, so you look at a configuration, and the same configuration where you switch the value of sigma of the spin at sigma, then the contribution of sigma and sigma x is going to be exactly a certain quantity and minus this quantity for this thing. Because everything else doesn't change, just the value at x gives you minus the value that it was getting before. So this is telling you that this big sum is 0. As soon as one of these values is odd, this big sum is 0. And if it's even, well, this is always sigma x to this power is always 1. So you are a product of 1. So you are just summing on the number of configuration 1. So you are basically just counting the number of configuration, which is 2 to the number to vg. So you get 2 to v of g times the indicator that sum of the nxy plus delta of x belongs to A is odd for is even, sorry, for every x in v of g. And this is exactly saying that the sources is A. So this is exactly 2 to the v of g, sum over n in omega g of w beta of n. So this is a very simple observation. And let me give you one consequence, which if I ask you to prove it, you would not be able to prove it without that. In fact, it is doable, but it's... so just example of an application, just to tell you how powerful this is going to be, it's just to illustrate this. If you look at this quantity, look at the product of the spins, look at the average. Well, it's larger or equal to 0. And this is called the first Griffiths inequality. And the first proof of that was not very, very pleasant. And here it's completely straightforward. Why? Because you are just summing positive quantities. Okay? Okay, we make a break. We start, let's start at 15, and I will stop a little bit earlier because it's also convenient for me. Okay? Okay, let's start again. So this is the first thing with the first application. Let's look now at plus boundary conditions. So what is changing in the case of plus boundary conditions? So you can define exactly like here. You can define z plus of g beta a, which is going to be exactly the same as before, except that it's h plus g sigma. So here, yeah, okay, good. And so what we are going to do here is that we are going to define a graph g delta, okay, which is going to be the following. So a graph which vertex set is v of g union a vertex delta, and this delta you do not take it in ZD. So it's some kind of additional vertex, or let's call it g. No, delta. And it's sometimes called Griffiths ghost vertex. And you can define G of X delta. You need to tell what it is. I'm going to write this as a sum over Y not in G. So that's something that depends on G of Gxy. So what is the idea? Somehow it's, how do you implement plus boundary conditions? You just say outside of your graph, all the vertices have spin plus. Instead of saying that there are many vertices, what I'm going to say, I have only one. It is plus. Then in order to keep the same strength of copying constants, you need exactly to say that Jxy is equal to this thing. Now, proposition. For any A in G, Z plus G beta A is equal to 2 to the V of G times the sum over N, but currents on G delta with sources at A of W beta of N. And here sources, be careful, the sources, I only define them on the graph G. So when I'm writing that, I'm not saying that delta is not a source, that the sum of the n xy is not odd at x equal delta. Okay? So it's only the sources on the graph. So it's important. So maybe write it like that. Maybe that's better like that. To really highlight this. Okay, and the proof is exactly the same. You have nothing more to say. It's really the same. So you understand that the source, like the random current representation, differs for plus and free boundary conditions only through the set on which you take your current. For plus boundary condition, you have your graph G, and you have an additional ghost vertex, which is connected to everybody. And notice also that if you take nearest neighbor, it's only connected to boundary vertices, simply because Jxy is going to be 0 for any y not in G if you take x, which is not on the boundary for nearest neighbor. But in general, it's connected to everybody. Good? So maybe it's time now to tell you, I mean, why is it a random current, why is it a geometric representation? Well, if I want it to be a geometric representation, I need to express the spin-spin correlations in terms of my currents, of connectivity properties of my current. The problem is that, okay, I have an expression there, right? I mean, so remark, I know that mu G beta free of sigma x sigma y, well, it's equal to the sum. So now I'm going to drop, when it's obvious, I'm going to drop the n currents. So I'm going to say just xy like that of w beta of n. And I can drop the 2 to the number of vertices because it appears both on the numerator and denominator. So I have this, but notice this is not quite, the set of currents on which I'm summing here is not at all the same as the set of currents where I'm summing here. So it's not, it would be much better if I would have something like, okay, this is the probability for a certain random current of something happening. But it's not at all the same because here it's not the sum over the currents, the sourceless currents with some special properties. It's just the sum of a very different currents. So I'm going to try to change a little bit that. And my ultimate goal is to be able to say that it's some probability of some connections between edges. So first I need to tell you how you are connected. I mean, what do I mean by connected? So let me define. If I take a current, we did use a percolation configuration on G by setting n of, omega of xy, which in fact I'm going to set n hat of xy in the future, to be simply 1 if nxy is strictly positive and 0 otherwise. So it's simply the trace of your current. So an edge is open if the current is strictly positive at this edge. And it's 0, and it's closed if the current is 0. Okay, so you are simply writing that. You are just keeping track of this. And now you can speak of connectivity in your graph. So this is how we want to speak about connectivity. And notice that somehow here, once again, this is what all these currents satisfy because there are sources at x and y that x is connected to y in n hat. Just the problem is it's not the same type of current. So the next lemma is going to allow us to get rid of this problem. It's the most important lemma. It's called the switching lemma. And the switching lemma is going to allow us to get rid of this problem of sources by switching sources between different set of currents. So let's take A included in V of G and XY included in V of G as well. And I'm going to look at the following sum. So sum, and I take F from the set of currents into R. So look at the sum over N1 with sources A and N2 with sources XY. So I'm going to sum on pairs of currents. And I'm going to look at the following observable. I want to look at an observable on the sum of the two currents. And the two currents, somehow I think of them as really it's two independent sums. So basically it's like I would be sampling two independent currents. I'm going to go back to that. So look at this sum, and my goal is to write it almost the same, except that I'm switching the sources of N2 to N1. So switching meaning really I put the sources on the other side, so the natural thing, you see, if you put two currents with sources XY, if you sum two currents with sources XY, well, you don't have sources anymore. Right? The sources really, when you sum currents, the sources, you take the symmetric difference. So the natural thing is to take the symmetric difference here. And I would like, that would be absolutely beautiful if I would have this thing, that I'm just allowed to switch sources for free. Right? The only problem is, you see, take for a moment the example of A being XY. Imagine that N1 and N2 have the same sources. When you switch like that, in the first sum you always have sources at x and y in both cases. Here you have 0 sources in both cases. But you see here, for instance, take the indicator, then for this thing, take the indicator that x is connected to y. Then it's always going to be 1 here, because x is always connected to y in N1 plus N2. But here, because there are 0 sources in both cases, then it's not automatic that x is connected to y. So it doesn't mean that there is something wrong, because here, of course, you don't have the same sources as here, but something fishy seems to be going on here. So you need probably to modify a little bit your graph, your condition here. And actually, the way of doing it is very simple. Is you are just going to add one thing, which is indicator, that x is connected to y in N1 plus N2 hat. So you need to be able to go from x to y on the sum of the currents. And then it's an identity. Okay, let me try to prove this, and then we are going to make a few applications. Try to prove a few applications of this. Okay. So let's look at this sum first. So let's call it 1, and this is 2. So 1, what I'm going to do is I'm going to define m to be n1 plus n2, and n to be I'm not sure, n2. Okay, I guess n2. Let's see with that. So we're just going to make a change of variable. When I do this change of variable here, I get sum. So the sources of m are just a delta xy. So you understand why I'm happy to do that, because it's going to be in both cases the same set of sources. I'm going to get f of m. And then I get here, if you look at this w beta of n1, w beta of n2, so w beta of n, w beta of m minus n, well, you can check that it's just w beta of m times a certain quantity, and the certain quantity is going to be the sum of 1 for n smaller or equal to m. Well, maybe, okay, no, I'm going to write directly the results. That's going to be simpler. So you get a w beta of m, and you get the sum over n, which sources xy, n smaller or equal to n. This is automatic. And here you just get 1. It's a very strange thing, but you just, when you write this guy in terms of, these guys in terms of this guy, you are going to get exactly that. It's very easy to get. Simply, well, maybe I should do this thing. So it's y is the product over x, over xy, sorry, of beta jxy to the n1 plus n2 xy over n1 xy factorial, n2 xy factorial. Okay? Here you see the m to xy appearing. So this is perfect. It's the product of a xy. You just make the beta jxy to the mxy over mxy appearing. And you get a product of a xy of m factor mxy factorial divided by n xy factorial, m minus nxy factorial. And this thing, you can exactly interpret it as a number of guys smaller than satisfying blah blah. So you can really do that. And you can do the same for the other sum. So 2 is exactly equal to the sum. I get f of m, I get w beta of m, and I get the sum for n this time, which is empty set, n smaller or equal to m of 1. But remember, I also have the indicator that x is connected to y in m hat. So what is the only thing I need to prove here? I need to prove that this quantity and this one are always equal. Okay, well, first thing, if x is not connected in m hat to y, so let's call this guy B and this guy A, then A, by definition, what is, there is no current smaller than M with sources at X and Y, because this current has necessarily X and Y are necessarily connected, so they would be connected in M because M is larger than N. So in this case, A equal to 0, and is also equal to B because in this case, X is not connected to Y, so you get 0. Now, if x is connected to y, then it becomes more interesting. So the simplest way of seeing that there are as many subcurrents with xy sources than currents with no sources is to map M to a hypergraph. So graph means multiple edges. So let's M be the graph with vertices Vg and with set of edges, which is just the set of xy with mxy positive. But what you do is you put mxy such edges. Okay? So between two vertices, you put as many edges as mxy. Now, how do you interpret these two quantities? Here is the number of subgraphs with sources at x and with degree odd at x and y, and here it's the number of subgraphs with degree even for every vertex, right? Is there a simple mapping between the two sets? The answer is yes. If x is connected by m hat to y, you can choose a set, let's say K, a subgraph K, with that the sources, or here in this case, the sources would rather be the degree. Okay? The two only vertices with odd degrees are x and y. You can find such a guy. You can just look at the construction I made at the beginning to say that you pick a path between the two. And what is the mapping between the set of sourceless and the set of guy with sources x and y? You just take the symmetric difference with k. So then what you do is for A equal B follows from the bijection. And it's simple to see it's a bijection because it's just an involution. The bijection which to a n gives n symmetric difference with k. Symmetric difference as subgraph. And that's the end of the proof. By the way, you see that xy here is not really specific. I could have taken B to be a graph. And then the condition would not have been that x is connected to y. It would have been that if I take the m associated to n1 plus n2, I can find a subgraph which has sources exactly B. So here, just a comment, if I take B here, here, I will replace this by M contains, or if you prefer, M, there exists n smaller than M with delta n equal B. And then I can do exactly the same thing because I'm just going to take this n as a k here. Okay? Good. Why is it good? Should rather say. Proposition. If I look at this quantity, and I divide by just the sum of the sourceless currents, what do I get? So just apply there to f equal 1. To f equal 1, sorry. To b equal xy and a equal xy. I get that the sum at the top is just the sum of the sources, current with sources x and y in both cases. So this is just the sum of the sources x and y in both cases divided by the sum of sourceless. This is just the square of the partition, the square of the correlations. So what did I end up doing? Notice that this thing on the left has a very nice interpretation. Define Pg beta to be obtained as follows. You take the trace of N1 and N2, where N1 and N2 are two independent sourceless currents with probability proportional to W beta of n. So there is a natural law, which is you take a sourceless current with probability proportional to W beta of n. So you take N1 like that. You take N2 completely independently. You take the trace of the sum. It gives you a random subgraph of your graph G. I call the law of this guy Pg beta. What is this quantity? It's just this. It's just this quantity. So I wrote the square this time. The square of a correlation as the probability of a connection in a certain random subgraph. This time is the square. And you are going to see there are very good reasons for that. Okay? Good. Just a question then. If I look at mu g beta sigma x plus, and I look at the square. By the way, when I wrote earlier that mu of sigma a was larger or equal to 0, I was very careful not to say strictly larger than 0. And the reason is that for any a which was odd, when I look at the product of the sigma a, I get 0 just by symmetry. Right? Because I have free boundary condition, I have global symmetry, I get 0. And this is very natural because, by the way, there is no current with an odd number of sources. It's just not possible. Right? So all of this was very coherent. Now with plus, it's not the case anymore. I can take the average under the plus boundary condition of sigma x. It's going to be positive. But the reason is because there is one source at x. But therefore, automatically, I get somehow a source at g, at delta, sorry. Okay? So just with this observation, if I look at the square of this thing, what am I going to get? Well, I'm going to get exactly the probability, this time in g delta, beta, that x is connected to delta, to the ghost vertex. So you also have an interpretation for the plus boundary conditions. And this is exactly doing the switching lemma in G delta. Let me give you other applications of this switching lemma. Let's look, for instance, take A and B disjoint. And let's look at mu g beta 3 of sigma A, sigma B. And I want to compare it to the product for sigma A and the product for sigma B. I mean the average for sigma A and the average for sigma B. You think it's going to be of which sign? It's going to be positive. Why? Well, this is what? This is one of the z. Let's drop the beta in the notation and the g. Okay. So it's one of the z empty set squared. Okay, because I have twice the partition function here. And what do I get at the top? I get z of A union B, z of empty set, minus z of A, z of B. Right? If I write the things with the partition functions. Now look at the representation in terms of currents. These guys, so it gives me 1 over sum of a sourceless currents. I'm not going to put the W beta, right? So I have the square of the sum like that, so I can write it as the sum over 2 currents, and then there is a weight. And at the top, it's going to be the sum over 1 current, which is A union B. The second current is empty set, minus the sum 1 current at A, as sources A, and 1 current as sources B. What can I do now? I can switch sources here, and I'm going to get the same thing. I get W, let me write them here. And I get 1 minus this indicator that there exists an n smaller than n1 plus n2, such that the boundary of n is B. But this is always larger or equal to 0. So you always get larger or equal to the product. And this is called the second Griffith inequality, and it's not easy to get, I can tell you, without this. It's the second Griffith inequality. One corollary of that, and by the way, if you take plus boundary condition, you can take A to be even. There is absolutely no problem with that, because you are going to switch, and just one of the sources is going to be delta, but it's fine. So one thing, what do I deduce on this quantity, for instance? From this type of things, what could I deduce on this? I can deduce it's increasing in beta. Increases in beta. In fact, this increases in beta. Why? Because when you differentiate that, you get the sum over xy of jxy, and then you get mu g beta f sigma a, sigma x, sigma y, minus the product of the two. So it's always positive. So this is a proof not using the random cluster representation that the thing is increasing. And this is the geodesic proof. That's the fastest way of getting there. Because remember the random cluster representation, to actually get that there was an ordering in P was not that easy. There was this holy criterion, and there was this couplings and so on. So here it's, I mean, basically we did it without any gap in the proof. Okay. So this is one thing we can do. Let me give you another thing. Let's keep doing some applications of the random current, and next week we will go into, so next week we will prove that the phase transition is continuous, that you have exponential decay in subcritical for any model, any Ising model. And we are going to use a random current representation for that. The week after, which will be probably the last class, we will see, maybe we'll do one more, but I'm not sure. We will do the fact that the phase transition is continuous in any dimension. But in order to finish today and to give you another application, let me try to look at the last application of the switching lemma, which is to look at what we call Husserl functions. So Husserl function is the following. I'm going to take U4 of sigma 1, I mean of spin x, y, z, and t. They are, you can define them in higher order. It's just, okay, what notation I'm going to denote like that for mu g beta 3, because otherwise I'm going to get crazy with the notations. So this thing is going to be sigma x, sigma y, sigma z, sigma t, minus all the possible pairing you can imagine. So you have sigma x paired with, x paired to y, and then z to t, sigma x, sigma z, sigma y, sigma t, and the last one is sigma z, x, sigma t, sigma y, sigma z. These are all the possible pairings. So this is called Husserl function. Let's try, this screams, now you can, maybe you start to recognize a little bit what screams to you switching lemma, and this starts to scream switching lemma. So do exactly as before, and here you are going to get z of x, y, z, t, z of empty set, minus products like that. What do you see? Here you are going to get z of x, y, z of z, t. You can switch the sources from z to t to the sources to x to y. So the second current you point to. Same thing, yt to xt and yz to xt. So when you do that, you are going to get 1 over the sum sourceless currents. And here you are going to get the sum for the first current is going to have sources at x, y, z, t in all the cases. And the second current is going to have sources, is going to have no sources. And you're going to get 1, this is what is going to occur from here, minus in the second case you are going to have z connected to t. In the third case, y connected to t, and in the fourth case, y connected to z. And that doesn't look like I want it to look. No, it's okay, maybe. Okay. You get that. And one thing which is easy to check is that with these sources x, y, z, t, so remember that N1 has sources x, y, z, t, this quantity is always equal to minus 2 indicator that everybody is connected together. X, y, z, t, all connected together. You can check, it's always equal to that. Basically because if you don't have that they are all connected together, then you have only 2 connected and 2 connected, okay? Because they need to be connected, x, y, z, t are the sources, so you need to have a pairing. If they are not connected together, then only one of these guys is going to fire, and you're going to get 0, which is indeed what you get here. And if they are all connected, all fire, and you get minus 2. So it's a very simple thing to check. So this is equal to minus 2, 1 over the sum of n1 equal n2 equal empty set. And at the top, now I know indicators that x, y, z, and t are all connected to each other. So what I'm going to do, I'm going to just do, I want to have sources here and here. So I'm going to rechange z, x and z. I'm going to drop them from this guy to this guy. So I'm going to get the sum. N1 is going to get sources y and, or let's say x and z. And N2, I drop the sources y and t, is going to get the sources y and t. So in this guy, indicators that x, y, z, and t are all connected together. This becomes here just indicator that x is connected to y. You can check that. It's the same. So when you do your random current, you get that. And when you do your switching lemma, you get that. Just trust me. This is really, just do it yourself. You are going to see it's very easy. So this is minus 2, sigma x, sigma z, sigma y, sigma t. Okay? So I'm just multiplying by the sum of this thing without the indicator. and divide it by this sum. So I'm here now, I get sum over sources n1. Okay, wait now. I get the sum at the bottom, and I get n1 with sources x and z, and n2 with sources y and t of wn1, wn2. And at the top, I get the sum over the same set of sources of currents of wn1, wn2, but I have indicator that x is connected to y in n1 plus n2. So what did I do between here and here? I just multiply and divide it by this quantity. Why did I do that? Because when I multiply by this quantity and I divide by this, I exactly see these two guys appearing. Okay? But now the good thing is that here you see the sum at the top and the bottom is on the same set of currents. So this you can once again interpret it exactly as we did before with this guy. Well, that's very good. Because here what you are saying is just take n1, now they are not sourceless, independent. You just say n1 with sources x and z and n2 with sources y and t. And you do exactly the same. You sample randomly n1, you sample randomly n2, you take the sum, you look whether x and y are connected, and you have that this times, so minus 2 times this times sigma x, sigma t, z, sigma y, sigma z, t, is equal to this u4 of x, y, z, and t. Okay, what do I deduce from that? Why is it nice? So U4, by the way, is, in quantum field theory, it's a very important quantity. Because it's equal to 0 when you have a field which is Gaussian, basically. When it's a Gaussian free field. So how big this thing is very important to note, to decide whether you are what we call a trivial field theory or not. So I'm going to go back to that next time. Let me just give you one application of this, and next time I will discuss, because this was the motivation to introduce this thing. So in fact, what is going to happen, so you can really interpret, okay, what's going to happen is that in high dimension, it's going to tend to 0. That's what I will start with next week. But let me give you a simpler application, but very nice one. Take a domain, and take G to be planar, and take X, Y, Z, and T to be found in clockwise order like that. Can somebody tell me what this thing is equal to in this case? So remember, I take two currents. One has sources X and Z. The other one has sources Y and T. And I'm looking whether X is connected to Y. All the guys are going to satisfy that. So the probability of X connected to Y when I have necessarily a path from X to Z and a path from X to T is going to be 1 in this case, in the case of G planar. So what I just proved, if you go back to the thing, I proved that sigma X, sigma Y, sigma Z, sigma T is equal, so this is equal to this plus this plus this minus twice this, because this thing is 1. So I just proved that this was equal to sigma X, sigma Y, sigma Z, sigma T, minus sigma X, sigma Z, sigma Y, sigma T, plus sigma X, sigma T, sigma Y, sigma Z. This is called a fermionic Wick rule. If I would have a plus here, it would be a Wick rule. This is a fermionic Wick rule, and that's something that you can deduce that was known for planar lattices for a long time, but it was using Grassmann variables and the fact the partition functions were expressed in terms of Grassmann variables. It was very complicated, and here you get it very easily. You can get it for 2 endpoints as well, and what you are going to get is that the 2 endpoints boundary spin-spin correlation are expressed as a Pfaffian of matrix having as entries 2-point correlation functions. So this is a very nice result. It's actually very useful if you want to prove, for instance, that the exponent, the boundary exponent is 1/2, for instance. I'm going to finish on that today, and I'm going to